Alright, hello guys and welcome back to the channel. So we are officially picking up where we left off in the last video, which was basically the first part of this chapter, which was nuclear physics, and now we're beginning with the more difficult, more comprehensive, and the lengthier part, which is radioactivity. So let's go through this together. Radioactivity is the process in which a nucleus becomes more stable by emitting radiation in the form of fast moving particles or high frequency EM radiation. So we know there are three types of radiation. This could be alpha or beta, because alpha is the helium nucleus that we just saw. Beta particles are basically electrons, or high frequency EM radiation, which is gamma. So in the EM spec videos, the one which was on the far right, the highest frequency, lowest wavelength radiation, that's gamma, and that's also emitted in the process of radioactivity. Sometimes radioactivity happens because the nucleus is too heavy. All right, so this is also true, but that sometimes the nucleus it has a lot of neutrons, so that's why radioactive decay happens. That's what's making it unstable. So sometimes that makes the nucleus become more stable. That's what radioactivity is. By the process of emissions, a more stable state is achieved. Now, the properties of radioactive decay. So the first property is called randomness, and it's a very important property. With randomness, we basically mean to say that we cannot say when a certain nucleus will decay, or if we have, for example, if we have in a sample of multiple nuclei, so like thousands or millions of nuclei, we do not know which one is going to decay. So that's what randomness means. So it's unpredictable. So cannot say when a certain nucleus will decay, or you can also say this, that's also acceptable, that which nucleus will decay in a sample. That's also fine. The other one is called spontaneous, which is called the spontaneity of radioactivity, which basically means it's unaffected by external conditions. So for example, like temperature or pressure, these things do not affect the rate of radioactive decay. It doesn't affect it at all. That's what this means. All right. So going on here, now we have this table that we'd like to fill out, and this contains a lot of what you're supposed to know. In fact, it contains all that you're supposed to know about alpha, beta, and gamma and their properties here. So let's start with this. So with this, the first thing that's written for alpha, beta, and gamma is its nature. So we know alpha particles are basically helium nuclei. So that's the plural of nucleus, helium nuclei. Beta are electrons. Gamma is high frequency EM radiation. The nuclear symbol for alpha is alpha 42. For beta, it's written like this, 0 minus 1, because it's an electron, so it has no, nucleon number. And gamma is just a wave, so this does not have any proton or nucleon number. Charge, so because alpha is a helium nucleus, so the charge is positive 2e, where e is the charge of an electron, right? So electrons and protons have equal charges. So plus 2e is the charge of this. And now if I have to do this, and again, this is something that would be given to me in an exam. The charge of an electron is 1.60 into 10 to the negative 19, which makes this positive 3.2 into 10 to the negative 19. This is coulombs. Similarly, electrons, so that has a charge of negative E, right? So negative the charge of an electron, which is 1.6 into 10 to the negative 19 coulombs. And for gamma, it has no charge. Penetrating power, so penetrating power is the greatest for alpha. Sorry, not penetrating power. I thought ionizing power. So penetrating power for alpha is the least, as it can be stopped. So it can be stopped by a piece of paper. Right, so something which is even less than 1 millimeters thick can stop alpha particles. Next, beta, this has a moderate range in air. So this can be stopped by few centimeters of aluminium. This is also going to be used a lot in, for example, in paper 2 questions where you'll have a counter and you'll have some source of radiation. In using these penetrating power properties, you would have to infer which sources of radiation are present. All right, so that's also something that you'll have to do in a lot of the past paper questions. And then gamma has the highest or the greatest penetrating power, because this can only be stopped by few centimeters of lead, and the chemical symbol for that is Pb. I'm writing this as lead. All right, so that's the idea of penetrating powers. What's the idea of ionizing power? So we've talked about this in the EM spec chapter as well, that when we talk about ionizing power, this basically refers to the idea that when radiation goes through something, it's going to knock off electrons and form atoms. So ionizing power of alpha is the greatest. And the reason is in the IGCSE syllabus, it's not in the O-level physics syllabus. So I'm just going to mention this for now. And that reasoning is basically this, that alpha particles have the greatest kinetic energy as well. Even though their speed is the slowest, their mass is really big because of those 4 nucleons, 2 protons and 2 electrons. So they have a lot of mass, and they also have like a really big charge, right? Positive 2e, which is this much. So they interact very strongly with matter, and they knock off the electrons, which leads to the production of ions. All right, and basically with each interaction, the alpha particles are transferring some of these energy in creating the ions, and they are slowing down. So the beta particles, because they are lower mass, they don't have as much ionizing ability, right? And because they're traveling faster, you can say they don't have enough time to interact, and because they also have less charge, so they don't produce as much of the ions. All right, and gamma, because they are uncharged, they have almost zero interaction, but they can still cause some ionization. This is something that has been asked in a few MCQs. So it doesn't have zero ionizing power, it has some ionizing ability still. Next, speed in air. So for this alpha, it's 10 to the 6 meters per second approximately. This is less than the speed of light. So this is 3 into 10 to less than 3 into 10 to the 8 meters per second. And since this is an EM spec wave, so we know that all members of the EM spec travel at 3 into 10 to the 8 meters per second. Next, their ranges in air. So for this, it's a few centimeters. You can say like 3 to 4 centimeters in air. This is a few meters in air, so like 1 to 2 meters for beta, and for this is several meters in air, which is like 8 to 10 meters. And when we talk about the applications later on, you will see how each of these properties are leveraged according to the use of that application. Let's go on. So penetrating power ionizing effect, this is some IGCSE stuff. So let's ignore this for now. Deflections in electric and magnetic fields. So how would these particles be deflected in fields of this sort? So we have alpha, beta, gamma in an electric field as well as in a magnetic field. So first of all, we know that gamma remains undeviated because it is uncharged. Because if it is uncharged, then the electric field is not going to have any effect on it. It would not be attracted or repelled by either of the positive or the negative plates. And similarly, if it's uncharged, then for this, when it's in a magnetic field, the requirement is that the particle must be moving and it must be charged. So even if it is moving, it's uncharged, so it would not basically experience any force, so it would not be deflected. For this one here, for alpha, it's pretty easy to see why and how they would be deflected, because alpha is positively charged. It would be repelled by the positive plate, attracted by the negative plate, so it would deflect in a direction like this. So that's how the alpha particle would deviate. Alpha was in red, so this is the alpha particle. Gamma undeviated, so let's make that. This is gamma, through and through, no deviation. And beta would be deflected in the opposite direction because it would be attracted by the positive, repelled by the negative because it's negatively charged. But this deflection would be much sharper. And the reasoning for this is that even though alpha has a greater charge, so it has twice the charge, but if you look back to that table, beta has 1/1840 times the mass. So beta has a much smaller mass. So that causes it to experience a much stronger deflection like this. Next, if we look at this one, so magnetic fields. Okay, so first let's write this. So alpha is attracted to the negative plate since it is positively charged. So unlike charges attract, beta is deviated by the same logic. Beta deviates more because even though it has less charge, it has a much lesser mass, causing it to experience a much larger acceleration, which leads to that deviation. For finding deviation in magnetic fields, we use Fleming's left-hand rule here. All right. And for this, there are a couple of things that we need to keep in mind. So first of all, when we're talking about Fleming's left-hand rule, always remember that the second finger, the middle finger, basically shows the direction of conventional current. So first, let's just get gamma out of the way because it's going to be undeviated anyway. And now, for example, if we talk about the alpha particles, so a cross shows that this is a field into the page, right? And now if we look at this, so we'd see that, for example, for the alpha particle, my field, my first finger points into the page, my second finger points to the right because that's how the alpha particle is moving. Conventional current is taken as the flow of positive charges. So first finger into second finger to the right. So I see my thumb deviating upwards like this. So this is how the alpha particle is going to deflect. For beta particles, again, I know it would deflect in the opposite direction, but how does Fleming's left-hand rule change? Because after all, it is still moving to the right. But the idea is that since this is a negative charge, this is basically showing electron flow. Conventional current is opposite to that. So if you have a negatively charged particle which is moving left to right, then your conventional current would actually be right to left. So while doing this for beta, your second finger would be pointing right to left like this. All right. So your field is still into the page. Your second finger is pointing right to left. So you'll see that your thumb points downwards. But again, by that same logic, the deviation would be much sharper with beta because of its lower mass. So for alpha, current is in the direction of velocity, since conventional current is the flow of positive charges. For beta, since it is a negative charge, it is opposite to the direction of velocity. Okay, next up we have the decay equations. So during alpha and beta decay, the nucleus changes to that of a different element. Nucleon and proton number are conserved in decay equations, and this is what we use to balance these equations. So for example, if I have alpha decay taking place, and let's say this is the nucleus, and let's say I don't know this, and it emits an alpha particle. So I know that for the conservation of the nucleon and the proton numbers, which are these numbers on the top and these numbers on the bottom. So for the numbers to be equal before and after the decay, if 4 is released, then this nucleon number must be a minus 4, so that a minus 4 plus 4 gives me a back again. Similarly, if this is z, and if it emits a alpha particle which has a proton number of 2, then this must be z minus 2, so that the minus 2 and the plus 2 together give me z back again. So that's the idea when I represent this in a general form like this. So write an alpha decay equation for uranium 23592 into thorium. Again, very straightforward. So if you have uranium 235 and 92, this is decaying, giving me an alpha particle which is 42. This is thorium. By the conservation of nucleon and proton numbers, this one must be 235 minus 4, that must be 231, and this one here must be 92 minus 2, which is 90. So that's how you do this. Next, beta decay. So for beta decay, the idea is again pretty much the same. This time a beta particle, which is an electron, is emitted. For the proton number, I can see, since the beta particle, for the nucleon number, I can see that since the beta particle has no proton number, it would not change this, so this would still be a. But for the proton number, because this is minus 1 here, and I want something here, when added to this minus 1 gives me z back again, so that must be z plus 1. So the plus 1 and the minus 1 again give me z. So that's the idea here. So something that you should be curious about and ask yourself about is this, that if we're talking about the decay of a nucleus, where does this guy even come out of? Because a nucleus contains just protons and neutrons. So where does an electron come from? So the idea is this, that in a nucleus, a neutron decays into a proton which emits an electron. Now let's face it, this is pretty difficult to remember with all of the other stuff that you're supposed to know. And it's even more difficult for me because I also have to teach A levels. So in that, you not only have beta negative, you also have beta positive decay. So the order switches around with that. And honestly, I've never remembered this. I just remember the basic principles and that gives me the answer. Now let's look here. So here beta decay happens, and this gives me an electron here. Right? So if you write this as an electron or as a beta particle, it doesn't make a difference. But because I want to show what happens in the nucleus, that's why I'm writing it like this. All right. So the idea I use is this. I know that with beta decay, in going from here to here, the proton number increases by 1. Now let's say that I mix up the order. And if I say if this is a proton, which would have this nuclide notation, so in going from here to here, this would become some particle which has a proton number of 2. But if we are talking about subatomic particles inside an atom, I do not know of any particle which has a proton number of 2. This means I've messed up the order, and the proton should have in fact been a neutron. So 1, 0, emitting a electron gives me a proton, causing the proton number to increase by 1. Nucleon number remains the same, and that's how I get my decay equation for a neutron into a proton. Write a beta decay equation for this sort of decay. So you have strontium 90 and 38, beta decay, so beta 0, -1. So I know that for its decay into Y, it must be the same nucleon number, and the proton number must increase by 1. And again, you can double check, 39 minus 1 is equal to 38. Gamma decay, so gamma decay is basically something which has no change in the nucleus. It's just some gamma which is emitted, and you can probably see why, because it has no nucleon or proton number, so there's no change in the nucleus, right? This is no different from this guy. So it's just shown like this, and you need to remember that all emissions that you have all increase the stability of the nucleus. So that's it for this video, and in the next video we'll pick up from here and go through the other remaining parts of this chapter.